So focus on this again. We got everything down here. We've got an expression for force. Given any little piece here, the force required to hold the piece statically in place is given by this expression, and location of each piece is very important. The radii of the pieces change as we go from the top down to the bottom of the tank. The height of each piece is the same, delta x, but we want an expression of these radii in terms of how far we are going to move each of these disks. Because the distance we're going to move these disks will be required in order for us to calculate work. So we will use a concept, basically a similar triangle concept or similar cylinder concept. Since each of these disks is parallel to the top of this cylinder, then wherever I happen to be here, I can think of this as another cylinder. The ratio of the little radius r to height of the little radius will be the same as the ratio of the big radius to big height. So, first of all, let's think back to this essentially cylinder we would have if we were to get rid of everything above it. So we get to this disk, and this disk has some radius we haven't calculated an expression for yet, and it has some height. And remember, we want to express this in terms of the distance that this disk will move upward when we remove it. And so to do that, let me say, alright, well, we want to move it to the top. How far down do we have to go to get to it? Well, starting from the top, moving down, the furthest down we could move would be 10. If we were to move all the way down to the bottom, we would move 10 meters. But we're not going to move all the way down. We're going to move down some distance, xi, corresponding to the particular disk. And so the distance down we're going to move is xi. And so now we want the height of this cylinder. So if we move down xi, the height of the cylinder is everything left over that we would have to move to get to the bottom of this. So this height plus this distance to get to the top must be equal to 10. And so 10 minus this height is the height of this smaller, wow, I've been saying cylinder this whole time. I have been meaning to say cone, and so I'm sorry about that. Anyway, you know what I'm saying, and I don't quite have time to redo this video, and it would take quite a bit to go back and do everything. So anyway, similar cones. The height of this smaller cone plus the distance that the small cylinder must move, small disk, small cylinder must move, those sum to 10. So this height itself has to be 10 minus the distance moved. And so this will be what we call little h. And because these are similar, the ratio of heights, the height of the entire cone, radius of the entire cone over height of the entire cone, that ratio will be the same as the small radius over the small height, the radius of the small cone as compared to the height of the small cone. And so we have a numeric value for that. We've been given the radius of the entire cone. We've been given the height of the entire cone. And so based on this logic, the radius to height ratio is going to be 4/10. And since we've come up with an expression for height in terms of the distance that we need to move this disk, we can re-express this ratio of little radius to little height. We can re-express this as follows. Take the expression for height, plug it right in here. I'm sorry. You would plug it right in here. And if we were to multiply both sides of this by little h, we would get 4/10 times little h. That simplifies to 2/5. So little r will be 4/10 little h. Little r will be 4/10 little h, which is 2/5. And now I plug in my expression for little h right here. So I will once again say, why are we doing this? Because we want to eventually calculate work. That's the goal here. And to calculate work, we have to calculate a bunch of distances that we move these disks by, supposing that we're just using a finite number of disks. And so, given that we have an expression for radii of the disks, and we haven't solved for these, or we haven't solved for an expression of this in terms of the distance these things will move. Well, we wanted to do that, so we went over here and we did that. So now we have that if we're at a position xi, then the radius of that particular disk will be equal to this in terms of xi, in terms of the distance that we must move this object. And so now what are we going to do? We're going to re-express force in terms of that by plugging in our little radius.